Well, good morning, everyone. Coming to you unexpectedly from home, here in bed with Harrison, who's not feeling great today. Do you want to say good morning, Harrison? Can you talk to Daddy's computer? You can't? Why do you not want to talk?
Because I'm sick.
Yeah, you are sick. You feel yucky today. Sorry if there's any sudden stops in the video here. I think we'll be all right, though. We're eating Cheerios and watching Curious George. So obviously this is not ideal because it doesn't let you ask questions, but hopefully it still clarifies some of the things that you were wondering about potentially, or just says everything a second time so you can hear it and really know it. So obviously at this point, you know IMF stands for intermolecular force. And that inter is important. It's not a chemical bond. It's the attraction from like one water molecule to another. And I've got lots of diagrams throughout this that you can see as you flip through your packet and kind of know that. But that's very important. It's not that chemical bond. So it's not talking about chemical properties. It's about physical properties. And probably the most important thing related to this is that it has to do with melting point and boiling point and state and solubility. Those are really the big three in terms of the properties. Vapor pressure and surface tension do relate to this, but those are asked about maybe once every 10 years or maybe on one multiple choice. But you're going to see melting point and boiling point, you're going to see state of matter, you're going to see solubility on the quiz, Friday's quiz, for example. That's tomorrow. And the following quiz and the test as well. So make sure that you're understanding how to apply it in that way. So just a quick comparison between bonds and intermolecular forces. So in HCl right here, the H to the Cl, that's our chemical bond. We're sharing electrons. If this was sodium chloride, the sodium to the chloride would be an ionic bond. If it was like sodium metal, sodium atoms to other sodium atoms, that's a metallic bond. So those are all bonds. Intermolecular force is this thing here that isn't chemically bonded to this thing here. How attracted to one another are they? So it's between the molecules. It's much, much weaker than a chemical bond. And it comes from the fact that there is an unequal distribution of electrons at some points. We have some partial positives and partial negatives. So it's not plus ones attracting to minus ones like when we have ions. It's not protons attracting to electrons. It's not sharing electrons. It's that we have an end, and let me draw this on here, an end that's a little bit positive, an end that's a little bit negative. So we basically have these weak magnets attracting one another. So there's lots of different types of intermolecular forces, and when you were in first year chemistry, we introduced a few of these but didn't talk about all of them. You can read this here, so I don't need to read it to you, but there's some important key words that we'll kind of go through as we use this. But the idea is that a dipole is important. That relates to polar things. An induced dipole relates to nonpolar things. Ions are obviously having to do with ions. And this one right here, London dispersion forces, which is going to be abbreviated as LDFs, we're going to use that one a whole bunch. So you're going to see lots of different abbreviations, lots of different new terms you have to be okay with. Dipole, that is what happens when we have a polar molecule. Induced dipole, that's what happens when we have a nonpolar molecule. And once again, we'll continue to be going through these as we start to use them. So as I just said, we have different types of compounds. So we can either have things that are polar, things that are nonpolar, or things that are ionic. None of this really relates to metallic compounds. None of this relates very much, except by contrast, I guess, to network covalent. So we're talking about ionic things, we're talking about polar things, we're talking about nonpolar things. So a polar molecule is polar because it has positive and negative ends. We talked about that in bonding. You need to draw a Lewis structure if you don't know off the top of your head if it's polar, and what you're looking for in your Lewis structure is if there is lone pairs on your central atom, or once again, if there's different elements bonded there. But those are just specific ways that we are looking for asymmetry. So a polar molecule, when you draw the Lewis structure, it's asymmetrical. Therefore, it does have positive and negative charges. It is, let me highlight here, unequal in its charge distribution. The opposite of that is nonpolar, where everything is symmetrical. So once again, it's technically determined by geometry, but if you don't meet any of these, where are we at here? Oh, there's the dog barking. Don't know if you can hear that. If you don't meet these qualifications right there, that means it's nonpolar. Something to know for nonpolar is if it is just carbon and hydrogen like that, it's nonpolar. So if there's carbon and hydrogen and something else, it's polar. Just carbon and hydrogen, it's nonpolar. And you're going to see that a lot. You'll see that on the quiz where it asks about hexane. In the lab we're in the middle of, ethyl acetate. That is a mostly nonpolar substance. From the bonding lab, you saw some nonpolar things when we used hexane as a solvent. That was our nonpolar. It was just carbons and hydrogens. And by being nonpolar, that means we don't have any positives and negatives, and the electrons are pretty equally distributed. When we have an ion, hopefully you know that, it's a metal with nonmetal. An ion, instead of being not charged, and instead of just having a little bit of charge or being partially charged, is a charge. You have a +1, you have a -1, or a +2 and a -2. So when we're looking to see, well, how or why are these things going to be attracted, or how strongly are these things attracted, it all comes back to, are they polar, nonpolar, or ionic? So the order that I have these explained in is based not really on strength, but kind of on importance. But it's not necessarily strongest to weakest or weakest to strongest or anything like that. So you can read everything that it says here. But hydrogen bonding's really important. If you done with your water? Okay, let me know if you feel sick. If you have hydrogen that's bonded to nitrogen, oxygen, or fluorine, it has hydrogen bonding. That's the most important intermolecular force. All it is a really strong version of a polar molecule. It's extra polar because nitrogen, oxygen, and fluorine are extra negative, hydrogen's extra positive. So you're looking for H, but not just any old H, an H that's on an NO or F. Dipole is really the same idea, but dipole-dipole attractions are, we have a polar molecule, so here's an example, an N that's negative, an N that's positive, and this negative attracts to that positive, which attracts to this negative, which attracts to that positive, which then attracts to this, and we've got an attraction here that's not even drawn. It has a permanent dipole. That just means there's always a positive and negative end, so these attract one another. The more polar it is, the stronger the attraction. But polar things stick together because they have positives and negatives. So we have polar, then we have extra strong polar if it's H with NO or F, that we call hydrogen bonding. Ions, like my sodium right here, has a charge, and things that have charge attract things that have charge. So that positive sodium, or even a negative chlorine, or a +2 calcium, or a -2 oxygen, or even a polyatomic ion like nitrate that has a -1 charge. That charge would be attracted to other charged things. So like sodium's attracted to chloride, but it's also attracted to the partial negatives on the oxygen end of water molecules. So this is what allows something like salt to dissolve in water, because we have our positive attracting to the partial negatives on my polar molecule. Once again, opposites attracting, and this is actually a little bit stronger than a dipole-dipole, because instead of a partially negative attracting to a partially positive, it's a full positive attracted to those partial negatives. So these, let me see, these are kind of like weak magnets, and this is an even stronger magnet because it's a full charge. The next one kind of gets into where we start to look at nonpolar things. An ion to what we call an induced dipole. So right here, this is showing an atom, but the same is true for a molecule. In nonpolar, overall, our electrons are distributed equally. There's no positive end, there's no negative end at all. But if you put that next to an ion, so this could be our same sodium there, that positive attracts the electrons that are in our molecule or atom and pulls the electrons to one side. So therefore the protons are kind of pushed away. So temporarily we have a weakly negative and weakly positive, or partially negative and partially positive end on something that by itself would be uncharged. So that's where this word induced comes from in this context, and really what the word means in general is a forced dipole. We don't really have a positive and negative end, but the ion made this neutral thing be positive and negative. So this isn't as strong as an ion to a dipole, because this isn't as positive or negative as my polar molecule, and it won't stay positive and negative like my polar molecule will, but there is partial positives and partial negatives there. So the next one here is a dipole to an induced dipole. So that is dipole. Remember, we're going back a few slides to, if you're back on the front page of the notes where it says types of IMFs. When it says dipole to induced dipole, that means dipole is there whenever we have a polar molecule. Induced dipole is there whenever we have a nonpolar molecule, just like it says right here, but I like that chart on the front because it kind of summarizes it as well. So because this has positives and negatives, and there's just partial positives and negatives, they force partial positives and partial negatives on this nonpolar oxygen, just like the ion did. Because this is a little bit less positive or negative than my ion, this is forced a little bit less positive and negative. But this kind of goes contrary to what most of you think, or what most of you have thought about with this, that there's no attraction between polar and nonpolar. There is. Polar forces nonpolar to temporarily be positive and negative. Polar forces nonpolar, therefore, to temporarily or partially attract. It's just not a very strong attraction, because this induced dipole isn't very positive or negative, and therefore that induced dipole to dipole attraction can't be very much. The weakest, but really the most important of all the IMFs, is an induced dipole, which is nonpolar, to another induced dipole, which is another nonpolar. It's so important, it's got its own name, called London dispersion force, but if you are ever writing about it, please just save yourself some time and just call it an LDF. If you've been in biology, AP biology, you may have heard the word van der Waals forces for things thrown around. We don't use that in chemistry. It's used differently and maybe not necessarily incorrectly, but not the way that chemists want to use it. So don't try to throw that word in anywhere here. Don't think, oh yeah, I remember that these are whatevers. I'm not even going to say it again. These are LDFs. But what happens here is I've got two nonpolar things, but because electrons are always randomly in motion, and we've talked about all of the things that go along with that, at any given moment there may be more electron density at one end than at the other. So the random motion made that very temporarily be a little bit negative and a little bit positive. Well, the fact that there was a little bit negative and a little bit positive on one of them attracted the other electrons and repelled the protons. So then that one was forced to be a little bit negative and a little bit positive. So we've got a random temporary dipole causing another dipole. So now we have these things that aren't really positive and negative, temporarily and weakly being positive and negative and actually attracting each other a little bit. And maybe the most important thing that people miss is right here. Even polar molecules can have random motion of electrons and can therefore exhibit LDFs. So if you're non-polar, the only type of attraction is LDFs. If you're polar, you have dipoles, but you also have LDFs. So this is just those pictures again. When it's an ion in a polar molecule, it's ion to dipole. When it is an ion to a nonpolar, it's ion to induced dipole. When it is a polar to polar, it's a dipole to dipole. And if that polar molecule has hydrogen on oxygen, nitrogen, or fluorine, it's an extra strong version of dipole-dipole called hydrogen bonding. If it's nonpolar with nonpolar, it is an LDF. They just put dispersion, but it is proper to call it London dispersion force. And then if it is a polar and a nonpolar, it is a dipole inducing a dipole. So, really quick summary. I'm actually going to stop this first video here, then we're going to make a second one so that they upload a little bit quicker to make sure they're ready to go by first period. But all molecules exhibit LDFs. So if the question asks you what type of things are there, you say LDFs for everything. And then if it's polar, it also has dipole-dipole. If it's polar with hydrogen on N or F, it also has hydrogen bonding. And if it's an ion, it can be attracted to a polar thing. It can be attracted to a non-polar thing. But we're thinking about how positive or how negative things are. So there is a difference in strength. Ions, full charges, exhibit the strongest attraction. Polar molecules exhibit the next strongest because they're permanently partially positive and partially negative. And if it's H with N or F, it's even stronger version of that. If it is nonpolar, it's temporarily and weakly positive and negative. So it's small but important, kind of temporary positives and negatives. So that hopefully kind of reviews those. And that's important because one thing you will almost always be asked to do is answer the question, what types of IMFs exist here? And it will say, list the IMFs and everything. And people start talking about just what the one thing has, but not the other. You have to say both. You have to say this compound has all of these, this compound has all of these. Then you go on to your next one. And you'll just answer that as a list. You're not going to ramble on about paragraphs explaining what they have or why they have it. If it's just carbons and hydrogens, you say that this C6H14 has LDFs. You're done. You're not explaining what an LDF is. You're not saying why it's an LDF. You're not explaining that my teacher was at home this day and this was a video and his son was watching Curious George. You're saying C6H14 is LDF. You're saying H2O is LDF, dipole-dipole, and H-bond. Then you're moving on. Do not ramble. Some of you, many of you, know that I'm talking to you right now. I am talking to you. So that's it for this first page. I'm going to pause it here or stop it here, upload it so we can get to the second video. The two.
All over your bed.
That's okay. So we'll get to the second one in just a moment.